Probably did this in your Calculus 2 class. So in this differential equation, notice that we have the derivative that's equal to something involving only the x. So what we can do is integrate both sides with respect to x. This is what it would look like. The integral of dy dx with respect to x, notice, would just be the integral of dy or y. And then we would need to perform the integration like we learned back in Calculus 1, in fact, on x minus 2 cubed. So that integral would be a 1/4 x minus 2 to the 4th. Notice our constant of integration. In fact, you'll notice anytime we have a first order differential equation, there should be one and only one constant of integration. So for solving this differential equation, we are told that when x is 0, y is 1. This is referred to as an initial value problem. Well, we can do basically what we just did, and that is integrate both sides with respect to x. And this time we can find our constant of integration by substituting. So we'll put a 0 in place of the x and a 1 in place of the y and solve for c. Therefore, we can rewrite our function as 1/2 sine 2x plus 1. So we are able to recover the exact function when we're given the initial conditions. There's another cute trick that we can use for solving initial value problems by using definite integrals. And it works pretty much like we just did, except it kind of saves us the step of having to do the substituting and solving. So what we're going to do is replace the variables x with some dummy variable. In this case we'll use s because that's what our textbook author does. And so we want to integrate both sides with respect to s, but we want to do the definite integral. This time we're going to integrate from 0 to x. And by the way, there's no special reason why we use 0 other than in this problem we want y of 0. So it makes sense to use 0. If we'd use some other value, we would then have to adjust back to 0 like we did in the previous problem. So anyway, here's the integral from 0 to x of dy ds with respect to x, which is y with the parameters 0 and x, and then 10 arctan s with the parameters 0 and x. Well, to finish out the definite integral, you substitute the top, you substitute the bottom, you subtract. And so here is the y of x that we're searching for. We know what y0 is because we're told right there that y0 is a 1. We can do the arctan of 0 ourselves and then do those substitutions. The y of 0 is a 1, and we come up with our answer. I'm going to do this one other example because of the interesting nature of the function that's involved here. So if we do the same thing that we just got through doing, integrate both sides with respect to s. On our calculator, we can try, this is a TI-89, we can try doing the integral of e to the negative s squared with respect to s. Now I just wanted to point out that on the TI-89, when you get the same thing that you typed, that is a surefire indicator that your calculator does not know what that integral is. And in this case, there's a good reason for the calculator not being able to perform that integral, and that's because there is no definite form for that integral. So there is no such thing as the integral of e to the negative s squared. So we'll give it a name, and that way from now on, if we ever encounter it, we can stick a name to it. However, we get this, okay, and again, all this is saying is you cannot do this integral. Leave it alone. But just like in the previous example, the y0 we know is 0, so we come out with our function being a integral of e to the negative s squared ds from 0 to x. We saw these first back in Calculus 2. This is a traditional example of a function defined as an integral. So we have a function, we have the integral defining that function. It's just that there's no new thing that this integral is equal to. Well, sort of. I'll show you in the next slide. People have made up names for this. Now maybe sometime we'll be able to go through and see why this works the way it does. I think that's in a future chapter in our book. However, notice here is the e to the negative s squared. This integral from 0 to x of 2 over root pi e to the negative s squared is known as the error function, or ERF. Now that's if it has this. Let me just point out the problem that we just did was the integral from 0 to x of e to the negative s squared ds. Well, you can see if there was a 2 over root pi here, there would have to be a root pi over 2 here. Which would make this a root pi over 2 ERF x. But anyway, here's another one that is probably new to you. The integral of sine s over s. Now we did learn something about this back in, well, in fact, way back in Calculus 1 when we were learning about the squeeze theorem and doing limits. We dealt with the sine of s over s. However, the integral of that is typically not something known to the calculators. And so we've given it a name. As you can see, we call it the SI or psi function. Here's a couple that might be somewhat familiar to you. The function that we traditionally call the natural log function, the ln function, is defined as this integral. And the arctan function defined as this integral. Typically, these two are programmed into your technology devices like TI-89s, and so it would be able to spit out arctan and ln.